All right, this is actually a pretty long packet, so I'm going to move fairly quickly on this. The first question was about the hot dog stand offering both small and large hot dogs. It's actually a simpler question than you might have thought. It's just a question of find the number of possible outcomes in the sample space, which means if I go and I order a hot dog and the person behind the hot dog stand says, well, what do you want? And I say, surprise me. How many different ways can it turn out? And the answer is two. I can have a small or I can have a large. Right? So the answer here is actually two. And the possible outcomes in the sample space are large and small. And when we're writing sample spaces, we usually put them in set notation like that. And then list all the possible outcomes. Hint, use a chart. Here's how this works. Okay? At least for me, the chart seemed like the most easy way to see this. You got two things going on, right? You've got two kinds of bread. You've got white and multigrain. And then you've got three kinds of meat, which was ham, turkey, and chicken, which means you've got ham on white, turkey on white, chicken on white, and then ham on multigrain, turkey on multigrain, and chicken on multigrain. So those are the 6 possible ways it can turn out. And if you're going to list them, we do that in this form here. Because these are all of the ways that it could turn out. Right? You could have multigrain and ham. You could have multigrain and turkey. And you can have multigrain and chicken. And that's it. Those are the 6 ways. Here, when I post this, I will leave a note saying you don't actually have to list all of them, because as it turns out, there are 81 different ways to do this. You've got 4 rooms, right? And each one can be painted white, yellow, or pink. And for each one of those white, yellow, and pink options, right? White, yellow, pink, for each one of those, for each one of these, you've got a set like this. And then for each one of those, you've got another set like this. So basically it's 3 times 3 times 3 times 3. And that's the fundamental counting principle, which we talk about here. What I was kind of hoping for this was that you would use a tree diagram, not to build the entire tree diagram necessarily, because that's quite a chore. But if you do build a tree diagram, it looks something like this. Right? You're starting with the 3 different colors for the first room. And even if I just think about white for the first room, look what happens. For room 2, I get white, yellow, pink. And if the second room is white, I still get white, yellow, and pink for the third room. And if the third room is white, I still get white, yellow, and pink. So just if the first 3 rooms are white, I have these 3. And if the first 2 rooms are white, but the third room is yellow, I have those 3 again. And if the first 2 rooms are white and the third room is pink, I get those 3 again. So here, if the first 2 rooms are white, I get all of these in the green, right? So for just having one room, just painting one room, there are 3 different possible ways it can turn out. Once I paint the second room, right, there are 9 possible ways it turns out, right, here, because I could do white, 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 yellow, white, pink, yellow, white, yellow, 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 pink, pink, white, pink, yellow, pink, pink. So in other words, for each one of these 3, I could paint the next room a different color. And then looking at this, if I say, well, okay, what about another room? Well, the second room was white, and I got all of these solutions. If the second room is yellow, I still get the same solutions again, the ones in the green circle. And if the second room is pink, I get all of those solutions again, and there were 9 in each one of these. So now I'm going to have 3 times 9, and in all of that, that's 27. And if I do the same thing, I totally ran out of room here, but if I did the same thing for yellow and I did the same thing for pink, this would all happen another 3 times. So the 27 that I've got listed here would turn into 81. And what would happen? How would you list them? Well, you would list them sort of methodically. White, yellow, pink, right? White, 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 yellow, pink, white, white, yellow, white, white, yellow, white, white, yellow, white, yellow, pink, white, white, pink, white, white, pink, white, white, pink, white, yellow, pink. And then do the same thing again, turning this into yellow, and then do the same thing again, turning it into pink, and then do the same thing again with all of these, where you keep all of these the same, but you just list them again for yellow and list them again for pink. Is that too much to do for this one problem? Yeah, but the idea of how you go about it or why it works, that's what this problem was for. So the answer here is 81. Here, using the fundamental counting principle, so again, how many different ways are there? A softball player bats 4 times in a game. Each bat results in an out, getting on base, or hitting a home run. So let's call it an out, getting on base, and hitting a home run, right? And again, they're independent. So after the first time at bat, you do it again. Out, base, home run. This time we've got 4 of them. It's actually the same problem as this one here. Okay, you're going to get 81 again. And like I said, you didn't have to list it. You didn't have to do a chart, because this time all you had to do was say, look, I've got 3 here, 3 here, 3 here, and 3 here. There are 3 ways for it to turn out the first time I'm at bat, 3 the second, 3 the third, 3 the fourth. Multiply them together, you get 81. Okay? So that was the first 4 questions. For question number 5, okay, let's see if we can zoom in on that a little bit. There we go. For question number 5, right, gambler places a bet on a horse. To win, he must pick the top 3 finishers in order. 10 horses of equal ability are entered in the race. Assuming the horses finish in random order, what is the probability that the gambler will win his bet? Well, that is 10 horses chosen as a permutation, right? We're going to choose 3 of them. What does that mean? Well, we've got 10 choices for the first one, 9 choices for the one who comes in second, 8 choices for the one who comes in third, and that's 10 times 9 times 8 is 720. Right? And for the gambler to win, he's got to pick all 3 in a row. So there's only one way to do that out of the 720. So the probability of winning is equal to 1 over 720. Here we've got a nature preserve. Has a population of 13 black bears. They've been tagged 1 through 13, so they can be observed over time. 2 of them are randomly selected and captured for evaluation. What's the probability that bears 3 and 5 are captured for evaluation? Well, let's see. We've got 13, and they can be observed over time. 2 of them are randomly selected and captured. It doesn't say what order they need to come in, right? So it's 2 of them. There are 13. Choose 2, okay? Which means we've got to do 13 permutation of 2 and divide that by 2 factorial. And the way we do this is to say there's 13 for the first one, 12 for the second. We're going to divide that by 2 times 1. Okay. And that equals 78. Okay. So what's the probability that we're going to capture 3 and 5? Well, the probability that we capture 3 and 5 is going to be 1 over 78. All right, let's look over here. 6 boys and 4 girls. Teacher randomly picks 6 students. What's the probability that he will pick exactly 2 girls? Well, I think